is going to work with Ahmet Alkan from Sabancı University. Consider the simplest matching problem in which we have an equal size of man and woman who have strict preferences over each other. In this setting, a matching mu associates each agent with a unique mate. And thanks to Alkan and Conway, we know that the set of stable matchings together with the man-wise Butterdan relation forms a lattice. That is, if mu and mu prime are stable, then their joint supremum and their meet infimum are also forming stable matrix. For an example, suppose we have 6 men, 6 women who have rankings over each other as depicted in here. So please memorize this picture, I will need that. The set of associated stable matchings, that is depicted in here. Each black box denotes the ranking of men over their mates. So in the man optimal stable matching, each man is matched to his first ranked stable matching, and in the woman optimal stable matching, each man is matched to his fifth ranked woman. Implication is that in this problem, there is no stable matching in which a man is matched to his sixth ranked woman. Although it may not be visible in here, there is no stable matching that is in which a woman is matched to her second ranked man. As for the motivation, the two-sided matching literature so far focuses on extremal matchings for good reasons, but we have equally good reasons to focus on equitable stable matchings. Although there is one way of being extremal, it's not clear how to be equitable. The breadth of possibilities calls for a foundational framework which has not been proposed previously, to the best of our knowledge. So to fill this gap, in this study, we introduce such a framework together with a new class of fairness notions. The framework, that's the critical notion. The primitive object that we use in our analysis is a matching tool that associates each problem, men's preferences, women's preferences, with a non-empty set of matchings. The first axiom, the first requirement is stability, telling that chosen matchings must be stable. The second principle is invariance under stability, telling that if for two different problems, the set of stable matchings turn out to be identical, then the chosen matchings must be identical as well. And a matching rule that complies with these two principles is called a stable matching rule. The invariance, let me comment on the invariance property, which might look innocent, but it interestingly bisects the existing matching rules in the literature into two. On the yes side, we have these three examples, and on the no side, we have these three examples. The common theme of the no side is that they are all based on explicit optimization of an objective function formulated via agents, rankings, or utilities over each other. What else could that be? We'll see. And the common theme of the yes side is that they are not based on explicit optimization, but rather uses the lattice structure of stable matchings, and they turn out to satisfy invariance under stability. Having said this, there is a way to convert no side into the yes. For this, the critical notion is that of attainable mates. Pick an agent I, then an agent J of opposite sex is attainable for agent I if there is a stable matching at which I and J are matched to each other. A sub I denotes the set of all attainable mates for an agent I. Going back to our example, for each man there are 5 attainable mates, and for each woman there are also 5 attainable mates. For a man, his 6th ranked woman is not attainable for him, and for a woman, her 2nd ranked man is not attainable for her. Well, how to use this notion to convert yes into no, no into yes for invariance. See an example. Focus on egalitarian stable matchings in the vein of utilitarian welfare matchings that minimize the sum of agents' rankings over each other is minimized. This matching rule would fail to satisfy invariance. To say this, suppose that on top of my preferences I have Natalie Portman. However, Natalie Portman is unfortunately not attainable for me. Well, think of another problem in which I move up my attainable mates on top of my preferences, keeping everything else identical. Imagine that each agent goes through this process of moving his or her attainable mates on top of their preferences. Then the resulting problem would be different than the original problem. The preferences are different. However, the set of stable matchings would be the same, but minimizers of this objective function might be different in these two problems. Therefore, it violates invariance. To correct for this, just replace rankings with attainable rankings in the sense that each agent focuses on his or her attainable mates and ranks them according to original preferences. Once we minimize this objective function, the set of minimizers would consider the set of minimizers, the matching rule that chooses the minimizers, that will comply with invariance. But this doesn't mean that it will be an interesting matching rule. In this case, unfortunately, this sum is constant among all stable matchings, so no stable matching is differentiated from others. The third condition, the main principle that we impose on a stable matching rule in this paper is modularity. Focus on matching rules that can be obtained as maximizers or optimizers of an objective function. We call such an objective function an assessment function, which maps each stable matching into a real value, interpreted as the fairness loss index. Then, such an assessment function is modular if for each stable matching, their total assessment equals the total assessment of their join and meet. And a stable matching rule is modular if for each problem one can find a modular assessment function, optimization of which results in the set of chosen matchings in that matching rule. Why modularity? In short, analytical tractability along with clarity and richness. Our proposition 1 makes this more visible. An objective function f is modular in this setting if and only if it can be written in this additively separable form over agents. It renders a natural interpretation. The social value of a matching is obtained by summing up the social value of matching an agent I with another agent J. As simply following from being additively separable over agents. As for analytical tractability, it follows from the beautiful paper of Picard that stable matchings optimizing such a modular function are isomorphic to min cuts of a specific flow network. And to my limited exposure to this literature, there are several fast algorithms used to solve or to approximate for this problem. It also, as we will see, it also allows for polynomial time solutions. Questions. We move into the analysis part. So the questions of interest. What is the ordinal or revealed content of optimizing a modular function? Is it clear and reasonable so that we can take it as an axiom? And as an economist, we typically observe just the chosen stable matchings, but not the underlying objectives. Can we identify them from the observables? So this is more in the vein of a revealed preference test we do in decision theory. Question boils down to come up for a simple test for modularity. We provide an answer, R2RM1 tells that a stable matching rule is modular if and only if it satisfies convexity. What is convexity? Pick two stable matchings that you have chosen. If there is another stable matching that can be represented as a mixture of these two stable matchings that are already chosen, then that mixture should be chosen as well. That mixture should be equitable as well. That is the usual phrase of, it's the usual formulation of convexity. What is the meaning of being a mixture in here? We say that mu is a mixture of mu prime and mu double prime if each man is matched to a woman at mu prime, that is his mate at mu prime or mu double prime. Put differently, we have mu prime and mu double prime. If the matching mu is obtained by a reshuffling of mates at mu prime and mu double prime, then, and if this matching mu is also stable, then it must be chosen as well. The stability, the requirement that reshuffling, that mixture being stable is critical for this definition. Examples, well, we have already seen examples of mixtures, join and meet. They are specific mixtures, but we have more than that. Suppose our rule picks up these two red matchings in this problem, then convexity requires the two matchings in the wings be chosen as well. There is a related notion of convexity in the lattice theory literature, implying that if two matchings in here are chosen, then anything in between must be chosen. I would better name it as connectedness. But notice that convexity is weaker than this notion of convexity, that is convexity, since we can very well choose these two red matchings without choosing the one two matching which lies in between, but which cannot be represented by mixing these two red matchings. Taking that into extreme, we can choose in this problem just the extremal matchings without choosing anything else that complies with convexity, although it would not comply with that lattice convexity notion. Well, we provide also another answer in the paper telling that a matching rule is modular if and only if a stable matching rule is modular if and only if it satisfies independence of irrelevant rankings, which mimics the IAA condition of error. This looks at, this condition is formulated in a quite different language, so I believe that it also sheds light on the fairness connotation of modularity, but that is in the paper. Now we have the frame. Let us demonstrate that this frame is fruitful, is good for generating new notions of equity. Go back to our example. This time in the black boxes, we have attainable rankings of men. In the red boxes, we have attainable rankings of women. Question is, which matching seems most equitable? Which matching seems at the median? If we appeal to existing solutions on the blue side, on the yes side for invariance, they unanimously single out this matching in which each man is matched to his second attainable mate and each woman is matched to her fourth attainable mate. However, one can argue that this matching in which each man or woman is matched to his or her third attainable mate, the median attainable mate is more equitable. Make notion clear, pick an agent I, think of his attainable mates, and name the one with a median rank as the median attainable mate. If the number of attainable mates is odd, then this agent is uniquely defined. If it is even, there are two such agents. Pick the one that is better in terms of agents' preferences. Okay? And now, based on this observation, let us formulate a new matching rule. Again, that will be formulated based on optimization of an assessment function. Pick an agent I, pick a matching, look at his mate at that matching, find his or her attainable rank, measure the distance of this attainable, measure the difference between this attainable rank and the median, the rank of median attainable mate. Do this for each agent, sum them up, and pick the matchings that minimize that value. So in short, we are trying to minimize the total spread from the mean attainable mates. This matching rule turns out to be a modular one, and it can be computed in polynomial time. Well, let us move from this specific example into let us try to generate a principle for equity based on this matching rule, or the observation that we may want to be as close as possible to median attainable mates. We formulate equity on dominance, telling that if a matching mu is chosen, then there is no other stable matching at which each agent is matched to someone who is closer to his or her attainable mate than his mate at the given matching, in the way of Pareto on dominance or stochastic on dominance. This time we ask for not being dominated in terms of being closer to median attainable mates. Again, just applying this single principle, we find out, we single out the median, we single out this 333 stable matching in our example. Well, you can say that, why don't we apply this principle as it is in general? Then, as shown in this example, we may end up with these 6 stable matchings, the red ones, and there is no particular structure among them. Even they do not form a sublattice. Okay, we pick these 2 red ones, but we do not choose this black one. So lack of structure and lack of uniqueness seems to be a problem in here. Once we, for example, look at our previous rule, the one that minimizes total spread from the median, it singles out a matching in here. And in general, imposing modularity on top of equity on dominance would bring analytical tractability as well as ease of interpretation. To make it concrete, we prove the following result. We ask the following question. Let us put convexity and equity on dominance together. What is the class of matching rules that we obtain? Again, they turn out to have this additively separable form. The objective function, the associated objective function, has this additively separable form, which basically comes from convexity. The implication of the additional restriction that follows from equity on dominance becomes that these individual assessment functions are unimodal, with mod being the median attainable mate for each agent. There is no loss of generality for replacing the median attainable mates with any ideal mate. Say that socially, we believe that for agent I, this man or woman is the most equitable mate. Then we can replace the notion of median attainable mate with the ideal mate by preserving the result. And the result tells that individual assessment functions must be unimodal with respect to the ideal mate for each agent. Extensions. We investigated how to extend the notion of convexity for general abstract distributive lattices, and I think we found the result. As an application, we can provide a counterpart of our result for many-to-one and many-to-many matchings. Let me conclude with a photo describing my feeling about this project. Here it is. There is a huge problem, and what we have done, there is a huge problem, the problem of finding equitable matchings, coming up with a framework to understand them. And what we have done is just a modest contribution to that problem. Thank you.